In this video, I will discuss Newton's method for solving nonlinear equations. Newton's method, also known as Newton-Raphson method, is in contrast to the bisection method from previous video. This is an open method for solving nonlinear equations in the form of f of x is equal to 0. Now, these open methods, they don't rely on an interval within which the solution is encapsulated. No, they just use information of the function f to iteratively improve on the estimated solution. So we start from an initial guess x0, and then we try to iterate using information on f in order to improve the accuracy and get closer and closer and closer to the true solution. Finally, we stop when we have achieved the desired accuracy. So the first thing you have to do when working with Newton's method is to choose an initial guess, x0, that you use to kickstart the method and which you will improve the accuracy of as you go through the iterations of the method. Now, the first thing to note here is that there is no best initial guess to start the method. Well, obviously the ideal guess would be the true solution, but that is not known. But it's also important to note that Newton's method, as we will see, is quite sensitive to the choice of the initial guess. So instead, we actually follow some heuristic rules in order to choose this initial solution. And the first thing that we try to do is we choose this initial guess to be close to the suspected solution if possible. So if it's computationally feasible or in a way feasible to make a rough plot of your function in order to get a kind of an idea as to where the function crosses the x-axis, so where this solution would lie, then this would be a very good idea, because then we can choose our initial guess to be, well, in the vicinity of this suspected solution. If this is not possible, well, then you basically have to make do with what you've got. But it's very important to stay away from, let's say, problematic regions that can cause very detrimental behavior of Newton's method. And such problematic regions occur, for instance, when you have discontinuities in the first derivative or in the function itself, or flat regions and local extrema of the function. Now, why that is the case, that will become clear when we look at how Newton's method improves on this initial guess. So improving on the iterate xi, well, how do we do that? So let's take a look at this sketch that we have over here on the right. So again, we have our function f of x, which is plotted against x. We want to solve the equation f of x is 0. So the true solution lies at the point where the function f crosses the x-axis, indicated by yellow over here. And let's say that we have an initial guess x0 over here. And now we will try to discuss how we improve the accuracy of the iterations based upon information that we have of the function f. So the first thing that we do is, well, we compute the function at the current numerical solution. So that's f of x0. Next, we compute the tangent line to this point. So the derivative of f at x0, or in the general case at xi. Now, if we have f in an analytical form, then, well, we hope to do this in an analytical way, and then it's possible. But sometimes this is not possible to get the analytical formulation of the derivative of f, and then we can use numerical approximations there. And more on that will come in chapter 8. So once that we have this tangent line, we will define the solution at the new iteration, so at the next iteration, as the point at which this tangent line crosses the x-axis. So from a geometric point of view, well, we see that we have here formed now a triangle. This triangle looks like this. So we have the the solution at iteration I. We have the solution in new iteration I plus 1. We know that the tangent of this angle, so the slope of this line, is equal to the derivative of the function at the previous iterate. That's because we drew this tangent line at the previous iteration. And we also know the length of this side over here. So in that sense, this triangle is completely determined geometrically. And just by computing this tangent, we can come up with this formula. So we find this relationship between each of these sides of the triangle. And if we recast this into this form, we immediately come up with a equation that defines the solution in the new iteration. So based on this geometrical picture, we can translate it into this formula over here. So that is how we improve on the iterations. We take the tangent line in the current iteration and we look at where that tangent line crosses the x-axis, and that will be our new solution in the new iteration. Again, we repeat this procedure. So again, in the iteration 2, well, we compute the function at this solution. Again, we draw the tangent line. We check where this crosses the x-axis, and that will be our new solution in iteration 3, or iteration 2 in this case. We can repeat this process, but we see that, well, in very few iterations, we are really gaining accuracy a lot. We're getting closer and closer to this true solution in a very rapid manner. We repeat this procedure until our stopping criterion is met, and you can again choose from a list of possible stopping criteria, either this estimate of the relative error, which should then be smaller than a certain tolerance which you specify, or the tolerance on the function value. So this should be very, very small. So in the true solution, this is equal to 0, or in the approximative case, well, we just set this tolerance on f to a very small value and stop when the function value evaluated at the current solution is smaller than that tolerance. Now, I already hinted that we should avoid certain regions of the function, and this will become clear right now. So local extrema and flat regions of the function, that's where the derivative of the function will be either exactly 0 or close to 0 when the function is quite flat or shallow. And if we look at the expression for the solution in the new iteration, we see that here we divide by the first derivative of f. Now, if that gets very small, this update, so the second term on the right, this will get very large. And this might cause instabilities in your iterative procedure. Let's take a look at an example here. So let's say that we chose to take the initial guess over here. And sadly, we see that the function here is quite flat. So we try to draw the tangent line. Well, we see again this slope, the derivative is almost equal to 0. It's slightly positive, but it's almost equal to 0. And if we try to find where this function would cross the x-axis, this is, well, very far away. And in this procedure, well, you can get really very far from the true solution in only a very small amount of iterations. And this is what can cause the Newton's method to really diverge and blow up. So the algorithm looks somewhat like this. We start by finding a suitable initial guess, x0, and then as long as the tolerance is not fulfilled, as long as our stopping criterion is not fulfilled, a small correction to the slide. So this should be in absolute values. So as long as this is not fulfilled, so as long as f is larger than this small number which we specify beforehand, we compute the function, we compute the tangent line, and we do the Newton update formula. Let's talk about convergence here. So I already said that from intuition, it seems that when we were looking at this animation earlier, that it seemed to go quite fast to that the numerical solution seemed to converge quite fast to the true solution. Let's now take a look whether we can get a somewhat more rigorous mathematical grasp on how fast this is actually happening. So how does the error decrease in subsequent iterations? Okay, so we know that in an iteration I, we will update the solution based on this formula over here. So the solution in the next iteration will be here. And we want to take a look at how the error, which at this point is equal to this length, how that decreases until this length. Now, as with many things, we can do this using Taylor series. So what we do is we make a Taylor series, a Taylor expansion of the function evaluated at the true solution around the solution in iteration I. And this looks as follows. So here I write it up until the zero order term, this first order term, so the first derivative times the difference in x, plus a remainder term. Now this remainder term on the figure can be interpreted as the length of this line over here. So that's the distance between 0 and where this straight line would end up at x is equal to the true solution. That is this remainder term. This remainder term is proportional to the distance between the true solution and the current numerical solution squared, and also proportional to the second derivative of f evaluated somewhere between xts and x and the numerical solution in this iteration. Okay, so starting from this Taylor expansion, well, we can proceed by realizing that f evaluated at the true solution is simply equal to 0, and by filling in this remainder term into the right-hand side of the equation. So then we come up with this formula over here. And what do we see? Well, we start seeing terms that look like errors. So this clearly, this term, and this term, well, that is basically the error that we have in iteration I. So that's the distance between the true solution and the numerical solution. So let's try to massage this expression a bit more, such that we also bring the error in iteration I plus 1 in there. So the first thing that we do is, well, let's divide everything by this first order derivative and rearrange the terms such that we go from here to here. So we just divide by this first derivative, and we group these two terms on the left here, and this one gets transferred to the other side, so that becomes a minus. Okay, so next observation is that, well, we have this f over f prime here, and we see that from the Newton update formula, f over f prime can be related to the update that we have in the solution. So this f over f prime can be simply written as follows. This is equal to minus the solution in iteration I plus 1 minus the solution in iteration I. So this is kind of the update that we're doing to the numerical solution, and I just copied the rest. So again, let's take a closer look at this equation over here. Here we see that this is the error in iteration I on the left-hand side. we see that we have minus minus x in iteration I minus x in iteration I. So those terms, they will cancel out against each other. And then we can take a look at what this thing is. Well, that's the true solution minus the numerical solution in iteration I plus 1. So this is simply equal to the error in iteration I plus 1. So in this sense, we have found a relationship between the error in iteration I and the error in iteration I plus 1. So repeating this formula here on top, we can take the absolute value of all the terms. We're not really interested in the sign of these errors. We're mostly interested in the fact that they are small or that they're close to zero. Whether they're positive or negative doesn't interest us that much. But we see then in this case that if x naught is close to the true solution, and if the following two things hold, so if the first derivative is not equal to 0, the second derivative is continuous, well, what that basically practically means is that this term is well behaved and doesn't go off to very large numbers or infinity. So if that is the case, then we actually find that the error in iteration I plus 1 is proportional to the error in iteration I squared. And that is what we call quadratic convergence. Now, in reality, this term will be smaller than 0 if we choose x naught close to the true solution. And then we get this nicely quadratic convergence. And what that means is, well, let's take a look at an example over here. So let's consider the hypothetical case that this term is simply equal to 1. In reality, it will not be equal to 1. It will be maybe equal to 0.5 or whatever. But let's just, for illustrative purposes, set it equal to 1. And let's take a look at how the error will then evolve within each iteration. And assuming that the error in iteration I is equal to 0.1, so 0.1, well then, in the next iteration, the error in iteration I plus 1 is equal to 1 times the error in iteration I squared. So the error will be 0.01. In iteration I plus 2, it will be 0.0001. So we see that here, the error goes down by orders of magnitude in every step. So we gain we double the amount of significant digits within every iteration. So we go from 1 to 2 to 4. So the error really decreases very rapidly as we progress through the iterations. Comparing this to bisection, for instance, from the previous video, where in every iteration the error was halved, we see that even though we start from a similar error here, that after a number of iterations, the error, well, it has decreased using bisection, but not nearly as much as Newton's method. An important side note to make here is that this quadratic convergence will only hold if these conditions are met. So let's take a look at a similar example that we also investigated for the bisection method. And this Newton root program is also included with the programs that are provided with the textbook. And actually you see, well, this is coded up as a function, but you see that Newton's method is really not that much of a involved or complex programming exercise. So what does this program do? Well, it updates the iterations based on the previous iteration and then a ratio of the function value with its derivative. It checks for convergence here to see whether the value of f is smaller than your specified tolerance. And then finally here, there's an additional test to avoid infinite loops in the case when Newton's method doesn't work that well. Now let's take a look at some numerical examples to showcase actually how performant this method is if it works. So looking again at this circle segment problem, we start the iteration, the first iteration. Well, we started at the initial estimate of x is equal to 3. We saw already before that the solution is somewhere around 2.4, which we determined using the bisection method in the previous video. But if we just plot this figure, we see it looks like this. We start the Newton's method from x is equal to 3. And then what do? Well, we evaluate the function, which is -5 almost. So that means that we're quite far from the true solution of fx is 0. So we evaluate the function, we evaluate the tangent line, and the crossing of the tangent line with the x-axis, that will be the solution in the second iteration. And that's what we see here. So we made a big step in x, and we're getting very close already to the true solution. And again, we do the same. So we evaluate the function, we draw the tangent line, and we then update the solution based on where this tangent line crosses the x-axis. And we see that here in 3 steps, we have, well, already reduced this function value below our tolerance, which was pre-specified at 0.001. So let's compare this to the bisection method for the exact same problem with the exact same stopping criteria. And the bisection method was started with an interval that the true solution lies between 2 and 3. And we started the Newton's method with an initial guess of x naught is equal to 3. And what we see over here is that in order to gain this much accuracy, so in order to satisfy this stopping criterion that the function value is smaller than 10 to the power minus 3, this needs 12 iterations using the bisection method. Whereas using Newton's method, this only took 3 iterations. Now, it's important to note that this is quite a low accuracy stopping criterion. So 10 to the power minus 3 here is not really saying much, because that's not very, very accurate. And computers can go to much, much higher accuracy. So let's take a look what happens when we increase the desired accuracy. So we decrease the tolerance by a few orders of magnitude. And that is what we see over here. So the only change I made is to update this stopping criterion, and I updated it from 10 to the power minus 3 to 10 to the power minus 12. And now the performance of Newton's method really starts shining through. So from the bisection method, this took us 42 iterations to be able to get the function value smaller than our pre-specified tolerance. Whereas using Newton's method, this took only 5 iterations. So that's more than 8 times fewer iterations than the bisection method. If we take a look at the amount of correct digits that we observe in the solution produced by each of these numerical methods, then we see that for the bisection method, so I have here the exact solution, that for the bisection method, well, if we're lucky, we increase the amount of correct digits by 1 in an iteration. So this really slowly, very slowly increases as we go through more and more iterations. Whereas with Newton, we can clearly observe here what is this quadratic convergence. So we start from 2 correct digits, so the 2 and the 4. Here we already have 4 correct digits. Here we have So this is 4, 8, 9 correct digits, and then, well, this is at least 12 correct digits. I only printed it out up until the first 12 or 13 numbers behind the decimal point, but this is already completely accurate. And we actually see that f evaluated at this is 0. This is actually the exact solution to the problem in floating point precision, at least. Let's take a look at what happens when we choose another starting condition. So I already mentioned that Newton's method can be very dependent, and the performance of Newton's method can be very dependent on which initial guess you provided with to start the iteration process. And well, here we have a stopping criterion, 10 to the power minus 4, but we provided both methods with different initial guesses from the previous slides. So the bisection method was started with an interval saying that the 0 should lie somewhere between 2 and 6, whereas Newton was told that it should start from x naught is equal to 6. The performance of bisection is not greatly impacted by this initial condition. So we see that after 14 iterations, it achieved a sufficient accuracy, which triggered the stopping criterion and hence indicates a converged result up until the accuracy that we pre-specified. Looking at Newton, we see that it starts at x is equal to 6. It jumps to x is equal to minus 107. It alternates then again to the positive x, about 5,000, minus 800. So you see it's really oscillating, taking enormously large steps in x, which indicates that Newton's method is having some trouble with this problem. Now, in this case, after a while, it comes back to a number around 4, which is relatively close to the solution 2.43. And after that, we will see very clear rapid convergence. So we see that in only a few iterations, again, we converge to trigger the stopping criterion. So once it gets close to the solution, Newton is very fast. But if it gets caught up somewhere, it can start oscillating, producing these very large, very small, or very negative solutions, and that can be quite disastrous at some points. So here it kind of recovered from it, but let's take a look at another initial condition. So what I did here is I start Newton not from x is equal to 6, but I started from x is equal to 0.1. We see that bisection, well, it also used a slightly different starting interval from the previous one, but again, this does not impact the performance at all. Whereas Newton, it's really, really struggling. So it starts from 0.1, it goes to large positive numbers, it goes to negative numbers, positive numbers, and then we see really here it starts really completely to run away. And this is typically a point where you start saying, well, Newton's method is diverging. We have to stop it, or we're just wasting computational efforts on computing total nonsense. So this is completely going away from the solution, which means that Newton's method is diverging clearly. Now, another pitfall is that the method can get stuck. For instance, around the local minima, where there is not even a root or a 0. So in contrast to bracketing methods, where you always have an interval in which you are guaranteed to have a solution, so to have a 0 of the nonlinear function, these open methods do not guarantee actually the existence of a 0 at all. And so this is illustrated in this case. So what we have here is a function x squared plus 2, which clearly does not have a real zero. So if you try to solve this, you have something like the square root of -2. So the blue line never crosses the x-axis. But we can nonetheless start Newton's method on it. So if we start it here around 1.8, what we will see is it tries to evaluate the function, it draws the tangent line, and that leads to a new solution. And again, it will keep on doing this. It will keep oscillating around this local minima indefinitely. So even when there is no solution around, sometimes Newton's method can get stuck around one of these local minima and that it really starts oscillating around it. So that's also very undesirable behavior, which can typically be avoided if you can somehow plot the function, so make a rough sketch of the function and see whether there is actually a root in the vicinity and whether there's no local minima that kind of cause this oscillatory behavior. Another example here is, well, let's further look at the sensitivity to these initial conditions. So here we have the function. F of x is the arctangent of x, which clearly has a 0 at x is equal to 0. And we can run Newton's method on it. So we start it here at x is equal to 1. It draws the tangent, so the new solution will be over here. Again, it draws the tangent, new solution will be here. And that's how it proceeds. And we see that after 5 iterations, well, we're really quite close to the true solution of x is equal to 0. Now, if instead of the initial condition x is 1 from the previous case, we started from a slightly different initial condition, 1.5, then let's take a look at the behavior of the function. So the behavior of Newton's method. So we draw the tangent line, new solution will be here. We draw the tangent line, new solution will be here. Draw the tangent line, new solution will be here. Draw the tangent line, new solution. Well, x really starts increasing here. We're actually moving away from the solution. And this is because we're running into these flat regions of the curve where there is asymptotic behavior, and the very low values of the first derivative of the function there really drive you away from the solution instead of converging towards the solution. So this is also something to be very cautious of. And so one more iteration, you see that it's really running away. So wrapping up on Newton's method, Newton's method is an open method, which means that it does not use a bracket or an interval where it tries to close in on the solution within that interval. No, it just uses a current estimate and tries to improve on that estimate using the value of the function at the current solution and its derivative. Newton's method has several pros and cons, and the main advantage of Newton's method is that it can be extremely fast. So if some certain conditions which we discussed are met, then it attains quadratic convergence. And quadratic convergence means that basically within every iteration, you double the amount of significant digits that you get correct in the solution. If it converges, then Newton's method is extremely fast. But that also brings us to the one of the cons, the downsides, is that it can be extremely sensitive to initial guesses, and a bad initial guess can cause the method to diverge. So it's not guaranteed to converge to a solution. It can diverge for certain cases. Also, a minor disadvantage here is that it's relatively expensive per iteration compared to the bisection method. So whereas in bisection, you only have to evaluate the function once within every iteration, here we have to evaluate both the function and its derivative within every iteration. So we see that, well, we have to evaluate the function and its derivative to calculate the solution in the next iteration. Now, this can be problematic if your function is very expensive to evaluate, if it's an error function, or if it's a function that's very hard to approximate, that can be problematic. But also, if you don't have an analytic representation of the function, well, then calculating the derivative analytically might not be possible, and you might need to do some approximations to this derivative. And one of those approximations is actually used in the secant method, which is the topic of the next video.